The agenda of this talk is going to be divided into 6 sections. The first is the background of superconducting devices. Then we validate our Wavenology circuit model with 4 benchmark cases. Number 1 is the single squid. Number 2 is the squid array. Number 3 is the ideal bi-squid model. And number 4 is the more practical bi-squid model. Okay. And then after that, we validated our core technology of the simulator. We have to develop the graphic user interface to enable the researcher to really do some design works. Okay. Then the advanced feature we're going to introduce next is the co-simulation of Squid together with the complex EM electromagnetic field in the real environment. And then I want to spend 1 minute to talk about introduce our company. And then I want to provide some live demo show to show you how to use the software to perform some real designs. Okay. So let's get into the first topic, background. When we talk about the superconducting devices, the first thing that hit our mind is the Josephson junction. So I want to use a good analogy to compare this to the Josephson junction with the p-n junction. Okay. So this is semiconductor devices, very well known. You just use a p-type silicon and an n-type silicon and attach them together and apply a bias voltage across it. And the phenomena is that the electrons will only flow along single direction. So this is more known as p-n junction and is even more well known as the diode. Okay, it formed the fundamental device for semiconductor industry. So for the superconducting, it's quite actually similar. You're just sandwiching a non-superconducting material layer with 2 superconducting layers. And the phenomena is the superconducting electrons were tunneling through this insulator. So this effect is named after Brian Josephson in 1962, and he received the Nobel Prize in Physics in 1973. Okay, so to demonstrate, you just apply a DC pump current along the 2 terminals of this junction, and it will start to oscillate on its own at a frequency from 50 gigahertz to 100 gigahertz. Okay, so a simple simulation validation will be if we apply a constant current to this junction, and then its voltage response, transient voltage response, will be shown here. Okay, so as you can see, it's oscillating on its own at a certain frequency. Next, researchers and engineers will start to find a good real application for this Josephson junction. So the first device they develop is to parallel 2 Josephson junctions, connect in shunt connection, and apply the pumping current. So this is called superconducting quantum interference device. And the nice feature about this device is it's extremely sensitive to the magnetic flux that is flowing through this loop. And because of this nice feature, very sensitive to magnetic field, we have a lot of good applications, novel applications. For example, low noise squid array amplifiers, high resolution squid magnetometers, and squid sensors for low frequency imaging applications. For example, you can put this device into the MRI coil, and also some other X-ray particle detector, and digital processor even, and B-field receiving antennas, as well as the magnetic sensors in outer space. Okay, so this is the application of the superconducting device. And in this page, we reference the hardware example from this IEEE transaction paper. So you can see that the squid has already reached a stage that it can be made in the laboratory already. For example, this is 32 serial bi-squid model with 32 cells. Okay, and this is a diamond shape with bi-squid as well, bi-squid array. It's in 2D. So the device, this kind of research has already got the theoretical model, and also have already got the ability to manufacture it with the superconducting materials available. And also, again, from this paper, it summarized that we basically have 2 major types of squid. One is the original simple squid, two Josephson junction. Of course, with the mutual coupling considered, you have to introduce additional device to control, to model this effect. But this is still the simple squid model. And with the bi-squid model, you just add a bridging Josephson junction connecting the two connections of this pair and apply another pumping current to make this effect happen. So when compare these two major type, you will find that the bi-squid has much better linearity compared against the simple squid model. So as I mentioned, that you have the theory, you have the modeling, you know what's going on, and you can even do manufacture it in the lab, but there is no commercially available software that can help the designer, help the front user to really streamline their design process and prototype their layouts, so that they can make some real designs and with very high efficiencies. Okay, especially on the large scale 2D squid array and in the 3D complex 3D environments. So that forms our motivation. That's why we developed this technology and want to broadcast into the community. So as planned in the agenda, the first model would be the single squid. Let's start from simplest. So it's just two Josephson junction with the two additional inductance. And then we verify this using the DC pumping current and use a constant magnetic flux from 0 to nanosecond with its magnitude change from -2 to 2. And we measure the voltage response of this 2JJ. And you will see the voltage has a slightly phase different, but in general it's oscillating in a similar magnitude. And we also show you the average of the 2JJ voltage compare against the voltage across the entire device. Okay, so they're slightly different, but in general not much difference there. So if you apply a low-pass filter to filter out this signal, you will see the response is pretty much like this. Okay. So next, let's compare this curve with what we obtained in a reference paper. So you will see they matches really well. There is slightly difference there, but that's due to our filtering function is not identical and it's not perfect. So there is slightly difference, but in general, these two curves are agrees very well already. Okay. And next, the model 2 is the array of squids. So if you mention about array, it has two approaches. One is the 1D array. You just make the loop connect one by one in serial. And the other is the 2D squid array. You can, all of them are parallel connected and you form a network. Okay. So you will have the response according to the flux change externally as well. So let's see how can we verify this. We use the loop array and normally their size is different. So you do have a distribution to describe its size change. For example, we use a Gaussian distribution. That means the very first loop is has a small size, and the very last loop has a much bigger size. And the distribution of the size change is following this curve. Okay, so we apply 20, 40, 80, up to 100 loops. You will see that this is the response. And we compare this against the reference data. You can see that the major peaks are quite similar. However, it's a little bit off when it's reaching the low level. This is because during the manufacturing, your Josephson junction are not identical. So you need to add a random factor to this curve. That means your loop size cannot be perfectly matching this curve. So you have a random factor. And the reason of this mismatch is because we cannot repeat the identical random factor there. So we just generate another random factor. So that that's why you see the major part is matching, but the lower part, due to the random effect, is not quite matched. But we do have a phenomenon that as the loop size increases, more loops will follow this curve more accurately, and the random effect can be suppressed, and you will see it matches better and better as you increase the loop, the array size. Okay, so that's how we verify this 1D loop array. Then model 3, let's move on to model 3. This is the ideal bi-squid. So this is the model used in the reference paper. This is what WCT has built. It's just a bridging with additional Josephson junction. Okay. And to here, this is obtained in the paper. You will see that when the pumping current is 0, that means if the bridging Josephson junction is turned off, it returns to the simple model. Okay. And if it's turned on with this pumping current add in, you will see its linearity is much better. And if we plot these two curves together, you will see it's almost repeating what has been predicted in the paper. So that's for bi-squid. The next model is actually more practical because each superconducting has the inductance, and the mutual coupling has to be considered as well. So you do need to additional parameters to control modeling all these effects. So that's why it's getting more complicated. But let's see how we verify that. Again, by turning it off, it returns to the simple model. But by turning it on, you will see it's matching the reference data very well. But you will see when we put these three things together with the simple model, ideal bi-squid, and practical bi-squid, you see that how it's improved the linearity, but it's not the perfect one. So you can compare these curves. All right. And the squid is only one of the advanced features. So that belongs to here, circuits, SPI circuits, and in the circuit 1, you can define your circuit schematically in the graphic user interface. So you see there's a lot of elements you can put in, and we have started to build in the internal models of the squid, 1D squid array, 2D squid array, and many others. Okay. So some highlighted features here is user can assign arbitrary loop position to each unit, and then we allow very flexible transformation of the squid. For example, each loop can have a different loop normal. Okay, and its cell center and its Josephson junction parameters, self-inductance and the mutual inductance can all be customized. Okay, and also the random factor, random variation can be considered as well in such software. We also support the external DC bias of the H field and also the simulation time delay. Because at the very beginning, this is transient simulation, at the very beginning, the DC bias has not been stabilizing the squid yet. So user can ignore that part and only consider when it's stabilized. Okay. So I want to mention a little bit more about this design logic of the GUI. At this point, we don't have the prototyped or materialized that what kind of parameter distributions of squid that is valid. So the logic is we allow user to fully customize, fully configure every parameter of your squid array, so that it's easy for you to do the research, to do the development. And once some benchmark, some prototype has been nailed down, we can easily start to integrate the predefined distribution, predefined parameters into our GUI, and to make the designer can design this thing more efficiently. Okay. And I want to briefly go through the GUI here. For example, this is a 1D squid array design GUI. You can have serial parallel. You can have all the other parameters to change everything you want to configure these parameters. You can even enter one by one to fully customize every site, every loop, every junction. Okay. And this is 2D. It's just more complicated, and you have all the parameters as well. I will cover this during the live demo show to demonstrate more about it. So that's about this GUI. Next, I want to talk about the another advanced feature that we can put this Squid device into the full 3D electromagnetic field simulation. So how we do that? the principle is combining 0D and 3D simulations together. The 0D is actually the circuit, the lumped element. So I want to demonstrate this in this way. Squid and Squiff is usually in very tiny. It's usually in micrometers. And especially in microwave and radio frequency regime, it's gigahertz. So its wavelength is usually centimeters or millimeters, which is much, much larger than the Squiff device. So we have to be very careful and very clear that for this kind of tool to be sufficiently accurate and valid, we need to understand the caveat. That means your lumped element is much smaller than the wavelength in the eyes of electromagnetic waves. That's how the circuit modeling is going to work. If your frequency is much higher than terahertz or even in the optical frequency, that means your device is becoming very large, and the electromagnetic wave do see this thing as a 3D structure. So the lumped element is not going to work, and it's not a 0D anymore. So in the 3D simulation, we just use the hybrid simulation engine, which combines FDTD, FETD, and discontinuous Galerkin time domain to solve for electromagnetic waves. And the core technology we combine these two is to using the field circuit port to fully and truly coupling the field and circuit in each iterative time step. And that's what we developed for so many years. And then let me briefly talk about how we combine these two things together. So for example, in this picture is showing in the 3D environment, you have two cylinders. And then the way you define a 0D element is very simple. You just pick up two terminal points and making sure they're connecting to the metal. And then basically that's it. Your 0D and 3D is done. But inside the 0D, the internal structure of the 0D can be described in two ways. One is using a graphic. It's more user-friendly. You can have all kinds of circuit elements. Just put two ports connect to the 3D, and you can define all kinds of things, as I showed before. The other, we also provide a dialogue for the user. But this needs advanced knowledge of using SPICE language. You can describe your SPICE circuits using the file, the text command. And this is actually the net list of your circuit. Of course, we have built-in circuits, Squid, to add for you to add it as well. And then you can add the 3D connection in here. So this is the dialogue way. Next, I want to demonstrate a co-simulation example that can combine the field and circuit. So for example, this is a phased array. We have a Wixom power divider with circuit separating the signal. And we have a phase shifter. We also have the radiation elements. In this case, it's simple enough, just a 4 rectangular patch antenna. But when we put all things together, you can see there's a lot of circuits that can be put in. We have totally 32 independent circuits, and each one contains a lot of internal structure as well, both digitally and analog. So by controlling these circuits, you can see we can achieve beam steering in one single simulation. Okay. So that's a quick example to demonstrate the co-simulation of field circuit. Next, I want to show the example of the field circuit, but the circuit is describing a more advanced device, which is Squid. So for example, this is the dipole antenna radiating with this green signal, sinusoidal signal. And I have a plane wave coming in, and I have a device, 20 by 20 loops of Squid. And this thing simulated together, you can see how the field interfere with each other. And the device is right here, very tiny. Because it's so tiny, the interaction is almost invisible. So, but the circuit did have detected the signal in 3D. As you can see, the incoming wave is definitely detected. And if you apply the low-pass filter, you see that it's returning to the incoming signal. Interestingly, by putting this in a special position, that's what we call a sweet spot, the simultaneously radiating signal by the dipole antenna is not detected at all. So that brings another interesting topic. So that's an example of apply it. And then eventually we want to achieve this goal is to, you have a RF device, you have a circuit device, no matter it's quantum or some other device, as long as you can describe it with the SPICE language, you can put it into the 3D environment. And then you do have readout circuits, you do have RF radiation elements that is surrounding, which is also small, but they are 3D. They cannot be accurately described by the circuit anymore. So you do need to model them in 3D way together with the circuit. Okay, and all of this device is tiny, but it can be put into the large platform. So eventually we can achieve a system level simulation with device, RF, and platform put together and simulate. We're an R&D firm founded in 2005, and we develop CAE and EDA softwares. Our founder is Dr. Qinghua Liu, who is a professor at Duke University, and we have a website. And our office location is right here in North Carolina. Okay, and we receive all the Small Business Innovative Research Funding and Small Business Technology Transfer Funding. And the word is the public information is available in the government website here. Okay, and our products actually, I introduced Wavenology EM today most. But the Squid is only one advanced module to our software package. We also have particle in-cell available. We can also simulate acoustic and a seismic wave, which is called elastodynamics. Okay, so we do have a lot of examples available in our website. As you can see, we have full wave SPICE feature, full wave nonlinear, and we can also simulate the other quantum device like memristor, and as well as the other examples. So please do, when you have a chance, visit our website and take a look at the more capabilities we have. So next, let's start to do the live demo part. So the first example I want to show is very simple. This is an empty project. Then I want to put a Squid device here, and I want to put a outside incoming wave, and I want to see how it's detecting this incoming signal. So this is empty, and then to begin with, I use the design tab. This is a very fundamental input to tell the software what is the basic setup. For example, unit, I want to millimeter, nanosecond, gigahertz. Okay, then I just continue. Background, I want to use as air, free space. And the boundary, I want it to be open. It's infinitely large. However, I do want to shrink the box a little bit more, so I know its exact position and size. I just use open at input position. I want it to be much smaller. And as you can see, the box, I want it just smaller to save some simulation time. And then the pulse, the frequency and pulse. We have a lot of functions available, but I want to use typical ones. Blackman-Herring's window function, 0th order, and I put it this way. Apply, and you can see that this is a signal I want to use. Okay. Then the mesh, I just leave it as default, and then the time, I know exactly how long I want to simulate in this case, and I also want to customize my own time step as well. So I just click apply. That's it. That's basically the setup. Alright. Next, I need to add in the source. We have all kinds of source right here. Dipole, plane wave, HE polarized. We have beams as well. You can also user-define external field coming in. So in this case, I use a plane wave, H polarized. And the direction I want it to be 90 degree in theta, 0 in phi. And I want it to be delayed for 80 nanoseconds, and I want this magnitude to be very tiny, sensitive. Okay, so if I plot this, you will see, okay, my signal is delayed this much, and then the magnitude is what I entered. All right. So if you click OK, you will see, okay, my indicator is telling me, okay, magnetic field along Z direction is propagating along X. Okay, and I can also put a field observer at this position, just to detect how much, what is the magnetic field looks like. Next, I start to add the circuit. As I mentioned in the presentation already, this is where you add. And create new circuit using GUI, and you just pick up 2 points. and you will see the circuit schematic editor is loaded up. And first of all, you need to put 2 terminals right here. And then you need a DC current source as the pumping current. And change it to current. And what you want to use your customized signal to DC bias. So for example, 0 is 0, and at 1 minus 1 picosecond, 2 picosecond, and very long, okay? So it's here 0, rise time is 1 picosecond, the magnitude is 2.2 e to the minus 4, then I just keep it. And you can see the signal, how the signal looks like as you enter all of this data. So that's the source, I put it there. Then next I need to do the 1D Squid. In this example, I just use 1D. So I need to right click, edit property. You will see this is the dialog I mentioned in the PPT. So you do have serial and parallel here. And this example just make it simple. I just use 3 loops. And I want the loop area distribution to be linear, and I have a formula to calculate that. So this can make the work a little bit easier. I just use small values. Okay, so I will have a distribution. Each loop size is different. Okay. Then I also have loop center. We do have built-in formulations already, but as I mentioned, we do need user feedback to really prototype and nail down what should be used. So we keep all the functionalities to be user input available. So you can add it one by one. And to streamline that process, we can also load from the external files. So for example, this is loop center. If I have the center cell center here, predefined in file, you can load it in. Okay. Then the loop normal is editable as well, but in this case, it's all facing along Z plus direction, so I just keep it that way. Josephson junctions, you can edit all of them, customize it. But in this case, I just keep it identical. You can also load from file as well. Okay. So Josephson junction, self-inductance, we load from file again. Okay, self-inductance, as you can see. Of course, this is only 3 loops. You can add it by hand, but if it's large scale, you can use the files. Mutual inductance, you can also load file. In this case, I'll do mutual inductance. And then everything is done. This is reserved for our internal test. And then the startup is, as I said, 80 nanosecond. So basically that's it. That's the edit of the Squid array. And then next you just need to connect this circuit by dragging it and touching the terminals. Okay. And then it's connected. And make sure that in order for SPICE to simulate, you need to have a ground. So you put this as ground, and make sure it's editing outside. The 1,0 is connecting to the outside. And save it and check it. And basically that's it. You will see the tiny loop there in the 3D. Okay? And then you can start the simulation by clicking this button, just go. And you will see the simulation give you the progress bar, simulating very fast. And now it's still calculating the field and the circuit. And after that, I need post-processing and do the Squid simulation. And now it's done. Okay? And all the results are here. Double-click circuit, SPICE circuit, and there is a transient signal. You can see the circuit. That's what you define right here, right? So double-click, you will see, okay, this is a signal I have. It does detect the signal. And if you zoom in, you will see, okay, it's a high-frequency oscillation. But overall, for the low-frequency signal, it detected this way. All right? So that's for the simple case. Very simple. Remember, in the slides, I show you the vertical placed dipole antenna. But in this case, let me just make it parallel to the y direction. And you will see that the circuit is definitely being interfered if you make the dipole antenna this way. So you can see the response is totally different. Okay. And you can also see that in the 3D that how this field is propagating and interfering each other. Okay. So let me plot that out. You will see the field coming in is radiating out and it's interfering that device. Okay. And of course, if you can have the simple 3D structure in this way, you can also load the arbitrarily complicated structure. For example, in this case, I have loaded a circuit with a source here and a receiving terminal on the other two sides. And I put the Squid device right between the two ground, the plate, right there, as you can see. Okay. In this way, it's right here. So you will see that this device is definitely being interfered by that as well. If I check out the signals, you will see at the very beginning time, this is definitely interfered by the Squid. And by the way, the input signal looks like this from this source. Okay. So with that circuit model and the 3D complex 3D, the user can really put this device into the real environment and see its performance.